Right. So, hi everyone. Welcome to this external speaker series in our machine learning optimization group meeting. And it's quite a pleasure for us to have today Francis Bach, definitely one of the leading figure in the world on the intersection of machine learning and optimization. Francis goes. I actually know Francis from way back when he did his PhD at UC Berkeley with Mike Jordan. And one thing I really appreciate in his way to do research is clear thinking. Is like he has a good way to be able to look at the essence of a problem. Sometimes go back to the simple, like let's say linear regression or just like simplest assumption to really get the good insight on the problems. And so now he's a researcher at INRIA. In Paris and also in the lab of École Normale Supérieure. And he's been doing work on many different topics. At the beginning, more on kernel methods. And then he did also a lot of influential work in sparse methods in machine learning. So he had a very productive go with these methods. And then later on, went back more on optimization in machine learning, like acceleration and these kind of things. I won't go through his list of many awards, but to be noted that I actually didn't know from his biography that he just was recently elected at the French Academy of Science. So congratulations, Francis. And so today he will tell us on the effectiveness of Richardson extrapolation in machine learning. Oh, and I forgot to mention that also many people in this group here has had close interaction with Francis. So Nicolas Leroux and Fabien Pedregosa and me, we all did a postdoc in his lab, and then I was a researcher in his lab. And so for us, it's quite nice to be able to now see what he's been working up since then. All right, Francis, the floor is yours.
Thank you, Simon, for the very generous introduction. So it's a big pleasure to be like in my room, but give a talk in front of friends in Montréal. So today I'm going to talk about something very simple. So no deep thoughts about deep machine learning. It's going to be super shallow, okay, super simple. And the idea is to relax after a few weeks of hard work. So everything I'm going to talk about is available on arXiv. Also have a blog post about it. And this is submitted to NeurIPS in a few hours. So the summary in one slide. So the two slides. So the idea that you want to estimate some quantity x star. So vectors. It could be your estimator. It could be whatever you want. You need to estimate, and you have a method that will approximate this estimator, this true estimate x star through xt. And you have a parameter t. T can be the number of iterations, can be some form of regularization parameters. And as t goes to its limit, 0 if you regularize, and infinity if you do if this is the number of iterations, typically you have some asymptotic expansion as written over there, where xt is x star plus some error terms that go to 0. And you have some dominant error term, g of t, and some lower order terms, h of t. So the idea of extrapolation and acceleration from the numerical analysis point of view is to try to use several iterates, okay, xt for different t's, and hopefully to get rid of the dominant term g of t. Okay, so if this is the case, you went from an error whose magnitude was at the order of g of t to something which is at the order of h of t. So if h of t is much smaller than g of t, you're going to win. So first solution would be to remove g of t if you know it, but that would be cheating because knowing g of t is pretty hard. So the goal is to combine iterates without the knowledge of g of t. So here I've put on the slide full knowledge because, of course, you need to know something about the method. And so as I will show you, we need to know how the way it converges to 0. So you have two types of behaviors to go to zero, or broadly two types of behaviors. The first one is linear convergence, so exponential convergence. And for this, you have the expert in the room. I think Damien, I saw Damien in the chat. So Damien Seger is here, and it could explain a lot what to do when the sequence of x of t is converging linearly to x star. You do like what is called Anderson acceleration. I think we call it regularized nonlinear acceleration. And at the end, you can remove the first order term, and this is how you get acceleration. And this is, I will let Damien, I'm sure you already mentioned it to you. And what I want to focus on today is on situations where the behavior of convergence is slower, and when the convergence is sublinear as a power, not like as a t to a certain power, and this is where people typically use Richardson extrapolation. Okay, so this is really the goal. How can I accelerate without the full knowledge of g of t, but just the type, the way it converges to zero? So the principle is very simple, and it dates back from more than 100 years ago. And so, so I'm looking at sublinear convergence. So xt is like x star plus some dominant term, t power alpha times delta. So if t goes to zero, alpha will be positive, and if t goes to infinity, alpha will be negative. And the idea is that you take a linear combination with constant weights, and the fact that you have constant weights makes it different from Anderson acceleration, where you also combine linearly the iterates, but the weights are not constant. Okay, they depend non-linearly on the iterates. So you combine with like constant factors, and if you choose the factors and the values of t, which are if they are well chosen, then if you do something like this, 2 of xt times x taken at 2 power 1 over alpha of t, and this is the expansion for 2xt. This is just copying from the first line. And this is the expansion for the other term, where I simply replace t by its value. And when you expand, this will get 2. You get t power alpha, and the 2 will cancel with that 2. And you end up with x star, which is preserved, and you have removed the terms in t power alpha, and you keep the terms in t power beta. Okay, so as I mentioned earlier, this is very basic. Okay, and this is really the whole idea behind Richardson extrapolation. Okay, so you combine 2 iterates, and then you're fine. So as an illustration, so around 0. Okay, so typically here alpha is often 1 and beta is typically 2, and then this is your expansion, and this is in black your iterates. Okay, x star is where you want to go. This is the first order expansion. Okay, for xt. This is the second order expansion for the first order expansion for x of 2t, and because you have a O of t square, then you have those like circles of width t square or constant time t squares. And as you can see, if those are the 2 iterates, so if you go from this one and jump on the other side, okay, by taking the symmetric with respect to x of t, then you end up close to x star, and you have removed the first order term. Okay, so this is really what's happening. So here's the key here, is that you don't need to know delta. Okay, so here you need to know the existence of delta, okay, with the power t, with t power alpha, but no need to know the specifics of delta. This will be taken care of by the extrapolation technique. So this has been used. Go ahead.
Do you need to know exactly the value of alpha?
Yes, you need to know the value of alpha so that you can do the constellation over there. And so if you know, so typically, I'm going to mention it later, but if you know, if you hope that maybe alpha is 1 or 2, you can take 3 iterates and cancel the first 2 order terms if you want. Okay? But if the power is something like 1.333 and you don't know in advance, it's not going to work. I don't know how to make it work. Maybe there are ways of making it work. maybe going to the log. There may be ways. Typically, I don't know of any situations where you don't know alpha, excuse me, but this probably this can be extended as well by going to the log, maybe. I don't know, but that's
you don't need to know alpha exactly. As long as your difference is less than beta, you still get the optimal rate.
So you need to know
the alpha you believe is true and the true alpha, if the difference between the two is less than beta, don't they cancel out?
No, because if for example the true alpha is a 1.5.
Oh no, it's a difference.
You need to preserve 1.5. Okay.
Yeah, that's right. Yeah, never mind. Sorry.
But yeah. So this was typically used first in integration. Okay, if you solve an ordinary differential equation, then often, if you remember the analysis, or if you do integration, then you model the function through the first or second derivatives. And this was used for those types of accelerations. And this was called Richardson-Romberg in that setup. And I'll come back to that later. All right, so what does it have to do with machine learning and optimization? And so the goal of this work, of this talk, is to really revisit machine learning techniques, mostly optimization in this talk, and trying to see why it can be applied and why it cannot be applied. So I will go over two types of problems. So one where the parameter over which I'm going to do extrapolation will be the iteration number, k, of an algorithm. So k goes to infinity. And I will study various forms of gradient descent and Frank-Wolf. Okay, so this is the first part of the talk. And then the second part of the talk, no, three parts of the talk. So quickly, you can also do this on the step size of your SGD. Okay, so now the step size goes to 0 to make sure you converge, and you want to get the biggest possible step size, and extrapolation can help in keeping a big step size, and I will talk about that. And then the last part will be if you use it on the on some regularization parameter. Okay, lambda will be the notation and goes to 0. Okay, you want to regularize less, and I will apply it to Nesterov smoothing. Okay, so lambda will be the amount of smoothing that you will have. So for all of those three elements, what I will present, I won't present all details, but all of this, you need some expansion of the form xt is x star plus the constant times delta. Okay, so this requires some asymptotic analysis. So in this work, I'm moving away from the non-asymptotic analysis, where everything is true for any given t, to the easier and simpler world and rewarding world of asymptotics. Okay, so I can start to play with limits. And this is what I'm going to do in this work. All right, so let's start. So with optimization. Okay, so xk, you have some iterative algorithm indexed by k, and for this to work, you need that xk is x star plus some constant vector over k, plus typically a remainder term in over k squared. So in that setup, extrapolation is simply taking for k even 2xk minus x of k over 2. And because of the constellations I was presenting in the first or second slide, then you get this new expansion. Okay, so this is asymptotic. So the big O is really the regular big O from asymptotics. So I think, when can you expect this to work? Okay, so as you can see, necessary condition for this equation to be true is that the distance between xk and x star is of order 1 over k squared. Okay, so but this is not enough. So it's necessary, but it's not enough, because you need to know that xk and x star are close, okay, at order 1 over k, but you need a specific expansion. So let me be precise. If you're on the left side, where x0 is converging to x star, but oscillating around x star, okay, the magnitude of those oscillations could be of the order 1 over k, okay? But if you apply extrapolation there, it won't work. Why? Because this expansion is not true. And in fact, for those problems, you better use like Anderson type acceleration. So this is a situation where Richardson should not work. Richardson would work in situations like this on the right side, where you do converge to X star, but you have a direction, okay, which you tend to follow, okay, with which is dominating the convergence rate. Okay, so on the right you can apply Richardson. On the left you cannot apply Richardson. So when I mean you cannot apply at the evolution of moment, you can apply it, but it's not going to work. It's not going to degrade performance, but it's going to simply do nothing. Nothing more than the regular algorithm.
Question?
Yep.
Quick question. I'm a little bit confused about the condition you showed in the previous slide, or the previous frame of this slide. You said that something about this norm being big O 1 over k squared. So I think you said it's a necessary condition?
Yeah, because if this is true, then this is true.
Okay. Why am I a little bit confused about this? So in the basic sequence of iterates, you have x of k, you have this 1 over k delta term, right?
Mm-hmm.
And you haven't yet used the extrapolation to get rid of it.
No, but my point is that if the expression is true, then extrapolation works, okay? And so what I'm doing here is trying to, so if you take your preferred algorithm, can you apply extrapolation or not, okay? So one first thing to check is that whether you get convergence of sk to x star as a power of k, okay?
Mm-hmm.
What I'm saying that just having the distance going down, having an upper bound, the distance as 1 over k, or here the square as 1 over k square is not enough, because you can be like this is like Nesterov type convergence, where you oscillate to the optimum, you will not get acceleration there. Whereas if you have a specific direction of convergence, which is exactly what this expansion is saying, then it's going to work.
Okay, so you're saying you just need more, one extra assumption about the dynamics.
Yeah, I mean more than this.
Okay, I think I understand now. Okay, thank you.
Right, so let's look at the three algorithms. So the first one is average gradient descent. So I'm going to make some assumptions. Of course, since I'm the super shallow, S is going to be convex and differentiable. Everything's going to be bounded, and I'm going to make my life easier by assuming that the Hessian is PSD at the optimum. Okay, so in that setup, it's known that gradient descent will be locally linearly convergent. Okay, and I'm going to consider the average version. Okay, so this is gradient descent, where I go down the negative gradient with some step size, and I'm going to consider averaging of all the iterates. And why people do that is mostly to provide robustness to the noise in the gradients. Okay, so this dates back from Polyak and Yuditsky, and often called Polyak-Rupert averaging. And the issue when you do this is that you start xk converges linearly to the optimum x star. Okay, but if you do averaging, you're going to lose this convergence, and you're going to slow down the deterministic part of the algorithm quite a bit. So you become robust to noise, but you get slow forgetting of initial conditions. The condition, can you do Richardson over there? And clearly this is the most nice, this is the nicest example for Richardson, because here the HT thing, the remainder term will be exponential. Okay, so let me be precise. So this is the thing. And the other beautiful thing is that in that setup, if you work on averages, Richardson extrapolation is in fact already well known. This is called tail averaging. So if you take yk over that, and you take k even, and you take 2yk minus yk over 2, this is 2 times yk. This is like yk over 2. The two constants are the same, and you can only get the sum from k over 2 to k minus 1. So this is just averaging the last k over 2 iterates. And this is well known. It's called tail averaging, and this has been used like for quite a while to indeed like benefit from robustness to noise and don't lose exponential convergence. Okay, so here, in fact, it turns out that people were doing Richardson without knowing it. Okay, and I can provide some expansion Okay, so with the assumptions I've described earlier on, so differentiability, convexity, and so on. And you have that the average iterate around the global optimum is of the form delta over k plus some exponential term. And of course, the rho will depend on the condition number, the local condition number of the Hessian at the optimum. And here the delta has a closed form expression, okay, which doesn't really matter because it cannot be computed. Okay, so this case highlights the fact that although delta exists, delta does not need to be computed and typically cannot be computed. And so here, I like it. This is really a good case because you go from 1 over k convergence before extrapolation, and after extrapolation, you remove this and you get back the exponential. This is really the best case scenario. It's not new. Okay, this was known from before. It's more like an illustration of what can be done with extrapolation. And so now in a basic simulation, so this is logistic regression, dimension 400 with 4,000 data points. So simple covariance matrix with decaying eigenvalues. Okay, and you can see, so xk, this should be yk here, sorry. Average on this, so this is the average iterate. So you get a line in this like log plot. So this is indicating convergence is at the power of k. You can check the slope is -2. And this is before extrapolation, like 1 over k square. And after extrapolation, you get like a very steep line, which is exponential around there. This is just for illustration. And in fact, for most of the examples, I'm going to provide like the basic analysis and then some illustration on like a small scale data. Okay. Right. So this is average gradient descent where things are particularly simple. Any questions on this one? No? Okay. So now let's move on to accelerated gradient descent. Okay, so this dates back to Nesterov, and the idea that for convex functions you can go from 1 over k to 1 over k square convergence rates. Okay, and unfortunately here we are exactly in the situation where iterates do oscillate around the optimum. Okay, so if you have ever run like Fista or Nesterov acceleration, you typically see the functional values go like this, okay? So they tend to oscillate a bit. And so both like Sue and colleagues in the continuous time, or Nicolas Flammarion and myself in the discrete time, have analyzed it for quadratics. And in fact, indeed, you get like a cosine times 1 over k. Okay, so indeed you get like oscillations that go down as 1 over k. You still get oscillations. And this is a case where Richardson will not give you any gains. And if you apply it, this is like on a similar problem as a slide from before. You get blue, this is before extrapolation. Okay, you can check, this is 1 over k square. Okay, so yeah, you can check. And after in red, you lose a bit. And typically you tend to lose like half of the iterations. Okay, so you're going to essentially converge like this one. If there are no consolations, you tend to converge like this one. Okay, so it's not useful, but it's not hurting. Okay, so this is really, in a sense, the worst case scenario for Richardson does not help. Now we can get to Frank Wolf. So we have experts in the Frank Wolf world in this audience. So
Francis?
Yep.
Just before you get to Frank Wolf, so somebody asked a question also, where they say, in the case of gradient descent, does linear convergence hold for the case of noise with Richardson?
Oh, yeah, okay, so for this one, so for tail averaging, okay, so at least, okay, for least squares, where things are easier, so tail averaging will converge to the global optimum for LGD. And the forgetting of initial conditions will be exponential, but of course the noise part at the end will be like as 1 over k because this is LGD. Okay, so this is for least squares, and this is like well highlighted by the paper of Jane, which I'm mentioning, by Jane and colleagues, which I'm mentioning here. And for beyond least squares, like for LGD, So we studied it a bit with Émeric Deleveux and Alain Durmus. So you will get forgetting of initial conditions exponentially fast, but then you will get around the optimum with a width of order gamma, typically after tail averaging. So for so averaging with a constant step size is not converging beyond these squares. Okay, so you get, if the step size is small, you get close, but you will always get up to the noise level. Okay,
Thank you.
okay. All right, let's go to Frank-Wolf. I'm going to minimize some function f on some compact set. Okay, and so the Frank-Wolf algorithm is depicted below. So you start from xk minus 1, you look, this is in your compact set, you look at the direction of the gradient, and you follow it as far as you can on the compact set. So you end up in a corner of the set. So here I've taken a polytope, so I get to an extreme point of the polytope. I call x bar that thing, and then I make a step towards x bar. Okay, I take a convex combination. Okay, the idea being that with a convex combination, I stay within my compact set. So this is like picture in equations. This is the first order Taylor expansion, which I'm minimizing over the set K. Okay, this is what I'm minimizing, and this is the iterates. Okay, so there's a bunch of ways of finding rho or rho K over there. So typically there are other like open loop schedules, like 1 over K or 2 over K plus 1, which I'm going to consider. Or there is line search, which is also typical, which I will not consider because it's a bit harder to analyze. And it's known that for those various step sizes, the convergence is of the order 1 over K, if you take the step size 2 over K plus 1 or with line search. And if you take the 1 over K step size, the best rates are of the order log K over K. And there's a nice paper by Martin Yagi on this. And the goal is, what is the effects of extrapolation? Okay, so here, of course, there are many other ways of accelerating Frank-Wolf. Okay, so I should mention the one by Simon and Martin about called like pairwise Frank-Wolfs. Okay, so this is a way to get like beyond the 1 over K rate. Okay, and so in this work, I'm going to present like another way of doing it. Okay, not as efficient, but not as efficient. It's like the result will not be as good, but there will be a bonus. Okay, and the bonus will be that, in fact, before extrapolation, 1 over K can be improved on. Okay, so this was a bit surprising to me that, in fact, the 1 over K was a bit pessimistic for Frank-Wolf, and let me go to that now. All right, so I'm going to, of course, make assumptions with 3 S's, because it's strong assumptions, sorry about that. And I'm going to have some polytope K. So I'm going to assume that I'm applying this to polytopes, which is essentially most applications are with polytopes anyway, or many of them. And I'm going to assume some constraint qualification, which I've put in quotes because I don't want to describe it. But the idea that you end up in the middle of a phase. Okay, so you want to avoid that your X star is really very, very close to an extreme point. Okay, so this is like classical in optimization to derive like some asymptotic convergence rates. And this, I'm assuming something like that. And of course, this is to provide asymptotic results. So if I were to go for non-asymptotic results, I would need to be a bit more precise and introduce a lot of notations. All right, so what you can show for the step size 1 over K is that this is Frank-Wolf. Okay, you start from x0 and you go toward extreme points. Okay, like this, and you oscillate and you end up in some X star. Okay, so this is the standard picture about Frank-Wolf. You get oscillations and you get closer and closer to the face. And this can be formalized, and with the assumptions above, is you assume like locally strongly convex plus polytope and constraint qualification, then you can prove that xk is indeed x star plus some directions delta, which should be orthogonal to the face where you converge to, plus some 1 over K square. Okay, So the first consequence is that there is no log. Okay, so asymptotically there is no log. Okay, so you convert as 1/k. Okay, so there is no log. So in the paper, if you're really interested, it does not contradict the lower bound in log k/k for that algorithm because of the asymptotics. Okay. Which your talk? Excuse me. I have to. Well, okay. All right. Where was I? Yeah. So it doesn't contradict the lower bound because it's only asymptotic. And so this is the first consequence. There's no log, in fact. And so for function values, okay, so you apply these to function values. You use the smoothness. You use the first order expansion of f. So gradient is not 0 because you have a constraint optimization, and x star is on the border, and you use smoothness to get the 1/k square. So this is like before extrapolation, 1/k, improvement over log k/k, but after extrapolation, you get 1/k square. So this is a case where Richardsons go from 1/k to 1/k square. Okay, so this is one improvement, which is a typical improvement for Richardson. So if you look for a very basic simulation, so still logistic, so this time on the L1 ball. So before extrapolation, so of course, like x-axis is log of iterations, and y-axis distance to optimum in log scale as well. Before extrapolation, you see a line, and you can check the slope is -1, and after you see a line of slope -2. Okay. So here, before I get the question, since I'm doing extrapolation, I may go out of my set. Okay, so this is a bit of a bummer that you may go out. So there are various strategies to go back inside, but which I don't want to describe. But simple rescaling will be okay. In most cases, you stay inside. Okay. So this is an affine combination. 2 - 1 is not a convex combination. The weight here is negative. So this is a situation where Richardson goes from 1/k to 1/k square. So now the funny one, and this was a surprise, and if you take the better step size, 2/k + 1, essentially twice as big, then you get some expansion of a similar format. Okay, so you get oscillations, of course, but the width of the oscillations here are not 1/k, but 1/k square directly. Okay, and this means that before extrapolation, the convergence rate is asymptotically, of course, 1/k square. Okay, so this was a surprising fact that, in fact, once you get close to the optimum, and this is where it's a bit what I mean by close, that as soon as you start to identify the phase you're going to converge to, then you enter the 1/k square regime for convergence. So this means that if you're already at the 1/k square regime before extrapolation, it's not going to help at all for extrapolation. Okay, so lab for Nesterov is not going to help. Yep.
I have a question. Was it none before, this 1/k local convergence?
I asked around, namely to Martin, Yagi, and Simon, and I got the answer, we don't know. Is this correct, Simon?
You asked me that? I don't remember, but
I have some proof.
Yeah, no, but I guess, but nothing comes to my mind, indeed. So yeah.
But I was surprised because I was running simulations, of course, like a MATLAB proof before doing the math, and I was getting that figure here. In fact, that figure. Okay, so here this is like same problem as before, but with a different step size, and the slope before extrapolation is -2, and I was disappointed by the fact that extrapolation was not helping. But it took me some time to realize that, in fact, the two slopes were already at -2. Took me a long while. Okay, I don't want to say how much, but and yeah, so I didn't know it from before, and probably it's known somewhere, but I reread the papers on Frank Wolf, and I haven't found. One of the reasons is that that step size is not classical. This is not classical, but this is like maybe from 5 years ago that people are using that step size. And but if you have a reference, I'd be more than happy to know that this has been done before. Okay, I was surprised. And
okay. Yeah, but so here in this plot, you do see that you get the -1 at the beginning with the oscillation in some sense, up to the dimension basically in this case, which is on the order of the 100, and then you get the -2 later. And so you're saying you get the -2 behavior once you identify the optimal phase, and you're just
because essentially the asymptotics, okay, the way the proof works is very basic. Is that as you get close to X star, you only your Frank Wolf points, okay, your extreme point will only be the extreme point of the phase, and you will always end up selecting those points, okay. And at the end, if you're in that situation, then you can prove that you get something of that form. Okay? So this only works if at the point where all of your Frank Wolf points that you select are always on the correct phase. So it's really once you have identified the phase. Okay, so in a sense, it's a bit similar to the pairwise Frank Wolf, where you get like a big leverage once you identify the phase. No, Simon?
Not really. So because pairwise Frank Wolf. So if you're in a phase, then you're already, because the always step Frank Wolf version and pairwise Frank Wolf, they get you to the phase. So and once you're in the phase, you're basically normal Frank Wolf. But here also, do you know about the parallax method or this kind of thing? Because this a bit of like one of the way to avoid the oscillation was to use the previous points, so that you move parallel to, because here you're oscillating like this, and you want to move perpendicular to it. And then there was a heuristic which was basically to use like the previous 2 or 3 points and going like this, but they had no convergence result, by the way. So that's kind of,
I think it's a bit similar, but it's offline. Okay, so here there is no you run. Okay, so here of course you run you run one thing, and in an offline way, like Anderson acceleration, you combine iterates. Okay, so the parallax thing which you are describing is more the online way, but probably it's called parallax. I didn't know about it. So
I forgot the name actually.
Okay, parallax is your
might be parallax. I don't know.
Okay, fine. Yeah, okay, so for Frank Wolf, yes, so it's a case where sometimes Richardson helps, sometimes it doesn't. And but I think what I like is that this project made me go asymptotic. And I think there is some like nicety or beauty in asymptotics. Things get easier, and it's very relaxing. Much less math as well. Okay, so now, so it's done for the number of iterations. Let's look at the 2 other ways of doing extrapolation. The second way is on the step size. So I'm doing a GD. Okay, so I'm trying to minimize some function f, but I have access to some stochastic gradients, which are called g prime at xk minus 1, zk the random noise which you add on your gradients, and you assume that the expectation over the randomness is giving you your full gradient. And the algorithm is simply you go down the negative gradient and you do some averaging. And so it's known that when you do averaging, you get more robust to noise, but you're not going to converge to the true optimum. Okay, so yk will not converge to x star. You will if you're quadratic, but in general you will not. And you converge to some y star depending on gamma. So I have some video. Hopefully it's going to work. So in red, this is with averaging, and in blue, without averaging. So in blue, you always oscillate, okay, because this is a constant step size. And in red, you're going to converge, okay, to a point which is not the. So here, the green point is the global optimum. Okay, so you do get like oscillation for the classical LGD and convergence for the average LGD, but to the incorrect point. Okay, so this is, and of course, the distance between that point and the green thing will be lower as gamma goes to 0. Okay, so if you get like a decreasing step size, a very small step size, you're going to be very close. The question is, can you do extrapolation? And this is what we have done with Émeric Diolveux and Alain Durmus a few years ago. And so here, what they showed is that the point where you converge, so this is why you converge if you do SGD with averaging, is X star, but plus some remainder term, which is proportional to the step size, gamma, and with some like higher order term, gamma square. So this means that if you take now two sequences, okay, if you run SGD with the step size gamma and SGD with the step size 2 gamma, and you do averaging, then this one will converge to Y star of gamma, this one will converge to Y star of 2 gamma, and now if you combine them, since everything is linear, you can see that this difference will converge to this difference, and because I've used extrapolation, I'm going to remove those gamma times delta term. So this is really like the classical example of using Richardson extrapolation. So before I present simple simulation, you can go further. Okay, so if you can remove the gamma term, why not removing the gamma square term? Okay, so this is what we have done. So you can combine 3 iterites. Okay, so at gamma, 2 gamma and 3 gamma. Okay, and with the proper weights, then you can check. You need to remove the first 2 terms, the terms in gamma, the term in gamma square, and you're left with gamma cube. Okay, and then if you do 3 times, why not do m times? Okay, so here first you can do it. Okay, so if you combine gamma, 2 gamma, 3 gamma, up to m plus 1 gamma, and find the proper weights. Okay, and so here the expert in the room can guess what it should be. Okay, so if I have 2 minus 1, then 3 minus 3, 1, why should be the next line when I do to the highest order, to the higher order? Any guess? It's a tough one. So let me help you. If I put minus 1, 2 minus 1, minus 1, 3, minus 3, 1, does it help? No? Okay, so the answer is 4 minus 6, 4, 1. So this is just the expansion, the binomial expansion of the power. So power 2 is 1, 2, is 1 to 1. Power 3, 1, 3, 3, 1. Power 4, 1, 4, 6, 4, 1. Okay. I have a daughter who does like high school math, so I'm deep into it at the moment. And anyways, not very important. The goal is that what's important is that you can go up to order m. Okay, so if you do that, then you remove the first m order terms. So you're left with gamma to the power m plus 1. But the caveat, there are 2 caveats. The first one, you have to run m times. Okay, you have to run n iterations. Okay, so you lose like a factor of m plus 1 iterates. Okay, so you cannot you lose some iterations, and of course the big O here there will start to explode. So this is well known when you do like those higher order expansions. Is that typically what is inside the big O will diverge with m, and typically diverge exponentially. Okay, so and I have observed that if you're too greedy and want to extrapolate too much, you're going to diverge. So let's look on a very basic SGD technique. Okay, so this is SGD on logistic regression, dimension 20. This is the distance to optimum after probably replications, I forgot. And this is before extrapolation, with extrapolation, and with second order extrapolation. And before extrapolation, you don't converge, okay, you get stuck. After extrapolation, you do get a bit lower, you still get stuck. And if you do twice in extrapolation, you go even lower, okay, and you would get stuck at one point, but I didn't run like long enough to see it. So this is one example where you can do this on the step size. Yep.
So what special thing is happening after 4 on your x-axis. Like before 4, everything, all 3 of them are having the same behavior, right? After 4, something happening.
Okay, so the way SVG is working is that you start from a point, okay, and you forget that point to oscillate around the global optimum, okay? So that point is essentially where you have reached the vicinity of the global optimum and where you start to see the asymptotic effect, okay? And so the asymptotic effect will start once you get there. So before that point, when you do extrapolation, you're simply losing, you're simply like, it's not helping, okay? So you do quite similarly. But as soon as you get to that point, when you reach the asymptotic limit, this one gets stuck, and those ones will get stuck, but lower.
Okay.
Francis, do you know of a way to get exponential plus sigma square over t?
Exponential plus, okay, so here, if you want exponential, okay, so here I've chosen situations where you're not strongly convex, okay?
Okay.
I think here, probably the eigenvalue of the covariance matrix of the Hessians are going down to 0, maybe as 1 over k square, so that you never see linear convergence. I'm not sure, but if you want, typically you do tail averaging to do this.
Right, but then we get only to near the minimum, right? But not exactly to the minimum.
That's a very good question, Sharon. Yeah, so you want exponential. You want to combine this plot with the plot from before.
Exactly. Yeah.
My answer: if you do tail averaging on this one, it should work. This is
even theoretically.
Yeah.
Okay.
Theoretically.
Yeah. Okay. Fine.
I don't have a proof, but I'm willing to bet that it's going to work.
Okay. I can try because we got stuck in this recently. So.
Okay. But so here depends what you mean by proof. So if you want a non-asymptotic proof, it's going to be painful. If you want the asymptotic proof, it's going to be easy.
Okay, I can try asymptotic.
Okay. I spent so much time doing this non-asymptotic proof that I'm getting old and fed up. And asymptotic is really like for babies and senior people, like very senior. So, okay. So,
all right. Thank you.
All right. So this is HGD. Okay. So essentially the goal, okay, of this paper is to say, okay, I've tried to revisit most places in learning and try to see where it can apply, and this applies there as well. And final thing is on the regularization parameter. Okay, so this will be on Nesterov smoothing. So again, Nesterov, another important word by Nesterov. So when you want to minimize some function f, which is a sum of a smooth term and a non-smooth term. Okay, so typically H can be the loss and G is the regularizer. This would be the usual sparsity-inducing norm setup. Or H can be the regularizer and G can be the loss, the risk, and this is for strutted prediction. So it's very common to have the sum of a smooth and a non-smooth term. So since it is very common, there are many ways of dealing with that. Okay, you can use proximal techniques, you can use some Frank-Wolf things as well. Okay, so here I'm going to focus on the Nesterov smoothing, which is an idea that dates back from Nesterov, 2005, and the core idea is to replace your non-smooth term by some smooth term G of lambda, and to choose G of lambda so that you become smooth. Okay, so typically 1 over lambda smooth. So as lambda goes to 0, the smoothness constant will explode. But of course, you want G and G lambda to be close in an infinity norm, and typically you get an error of O of lambda. Okay, so here, if lambda is too small, you're not smooth enough, and if lambda is too big, you're going to be too far away. Okay, so there has to be a sweet spot for lambda. And one classical way to get this like smooth version, so there are many ways, but the classical one is to do like inf convolution with a smooth function. Essentially, you replace your max by log some x. Okay, so I don't want to go too much into the details over there, but most examples I know of that are going to smooth a function are often of that form. You start for something non-smooth to get something smooth, okay? And this one corresponds to adding the entropy to the dual, which is very, very classical. And you can check that for this one, indeed, it is 1 over lambda smooth, and the error is of the order lambda times log2, something like this. Right. So what is Nesterov smoothing? This is like replacing G by G lambda and minimizing H plus G lambda. And since H is smooth and G lambda is smooth, then you get a smooth function. And now you can look at the error rate. So you lose lambda because of the approximation of G by G lambda, okay? Then this is a convergence rate of accelerated gradient, 1 over k square, but this is multiplied by the smoothness constant, which is 1 over lambda, coming from there. And if you optimize over lambda, you get a lambda, so it should be proportional to 1 over k, and you get the right 1 over k. This is very classical 1 over k convergence rate for Nesterov smoothing. Can be attained by doing extra gradient on the primal dual problem. So there are many ways of getting this 1 over k for that type of problems, but this one is really one of the earlier ones and a simpler. And of course, you beat the usual like subgradient technique, which is in 1 over root k. So this is like a one-slide review of acceleration. So now the question is, can you use Richardson? Okay, so I'm going to use Richardson. Why? Because I have this. Okay, G minus G lambda is of the order O of lambda. So maybe here I get some direction of convergence. Okay, and in fact I do. And for this, I'm going to make some assumptions, of course, to make my life easier. So I'm going to assume G is polyhedral. Okay, so if G is a regularizer like L1 and infinity and so on, and if G is the loss, like structured SVM, for example, or any form of SVM would work. And I'm assuming I'm doing some entropy smoothing or quadratic smoothing in the dual, because this corresponds to inf convolution. And what I was able to show is that if you take the minimizer of H plus G lambda, okay, and X star the true minimizer, you do have such an expansion. Okay, there is a closed form, well, closed form. There's a formula for delta, which of course depends on quantities which you don't know, and from that you can get this formula that X lambda is X star plus first order term plus lambda square. So good candidate for extrapolation. Indeed, so if you do extrapolation, which is that term, then you remove this lambda term, and if you apply F, okay, you get back you get lambda square. Okay, so now if you do the trade-off between the error with G lambda, okay, and the error when you do the Nesterov acceleration on the smooth version, this is unchanged compared to before. This one is improved from lambda to lambda square. Now you change the trade-off. Okay, this is smaller now, so you can take lambda being smaller. Okay, and you get 1 over, not bigger, 1 over k to the power 2/3. And now you can change, you go from 1 over k to 1 over k to the power 4/3, so you gain a bit more. So now why not stop there? So you can do also M order expansion, okay, and you can check that if you do the M order expansion, you replace lambda power 2 by lambda power m plus 1, okay, and then you get a new rate of that form, and when m grows, you get 1 over k square. Okay, so essentially, if you are willing to do Richardson extrapolation to a high enough order, you can go back to 1 over k square. But of course, as I've mentioned before, first, the constant in the big O will explode in M. And secondly, you lose iterations. Why? Because you need to combine several smoothing parameters. Okay, so you have to take, if you do like one step extrapolation, you need 2 iterates. If you do M step, you need M plus 1 iterates. Okay, so in the In the simulations I'm going to show next, I'm taking into account the fact that I need more iterations. All right, so here, simple simulation on penalized lasso. I forgot the dimension, probably a few hundreds. So on the left, the goal is to study x of lambda. Okay, so here I'm optimizing up to convergence, and I'm studying the behavior of x lambda compared to x star. And on the right, it's studying of the algorithm. So let's focus on the left part at the moment. So this is like in the x-axis log of the regularization parameter. Okay, so here strong regularizer, here very small regularizer. And since I have a log-log plot, if I see lines, this corresponds to like lambda to a certain power. And you can check that before extrapolation, this should be a line of -1. Okay, more or less, yeah, -1. You can check that if you do one step, it's -2, and then as you get more and more like orders of Richardson, you get like lower and lower, but you start to get like not a good behavior at the beginning. Okay, so this is like in a sense to be expected, and just to highlight the fact that you see the behavior in some reasonable problem. Then on the right, I'm running Nesterov acceleration. Okay. And here I'm studying the distance to the optimum after k iterations. So here I'm cheating a lot. Why? Because so as you remember, you have this smoothing parameter lambda, and it should depend on k. Okay, so typically this is one of the annoying things about like Nesterov smoothing is the fact that you have to select the smoothing strength as a function of the number of iterations. Okay, so there are ways of linking them, but here what I've done is I've run like with many lambdas, and I take the inf of all like runs for all lambdas. Okay, the minimum of all curves. So this is just to assess the effect of choosing the best lambda for a given k. It's a total cheat, but I was too lazy to do more at this point. Okay, and so what you can see, so this is essentially like a lower bound on the benefit of using Richardson. So before Richardson, you get like a line. You can check the line is approximately of slope -1. Okay, you go from 2 to 4 to 4. So let's say -1. And after you do Richardson, so you improve the slope. And if you do like 3 times, you improve the slope, but you start to lose at the beginning. Okay, so this is the effect of the constant. You get a better behavior there, but a worse constant over there. All right, so this is it. So this is like the summary slide. So the idea of the talk was to look at various situations where you could use Richardson extrapolation. So I've highlighted 3 places. One where you extrapolate over the iteration number of an algorithm, okay, and then k goes to infinity. And for that, I've presented like various algorithms based on gradient descent. And for acceleration, it was not working really well. For average, it was really the poster example. And Frank Wolf was a bit mixed. Then I looked at cases where you send the parameter to 0. Either the step size is LGD, which plays a similar role as the regularization parameter. Okay, and for those, you get also a good behavior. You can apply this to ridge regression. Okay, it's in the paper, but it's something which works a bit. So here the key here is it does require asymptotic analysis. Okay, so it's a bit different in flavor from the classical bound that we have in optimization, where the goal is to prove like a global bound, but we don't care so much about the equivalent. So here, for that type of problems, we do need the equivalent. Okay, so doing it asymptotically is reasonably difficult. Doing it non-asymptotically would just be a big mess with constants. Okay, but this is doable, but that will introduce quite a few constants. And of course, this can be done in other problems. Okay, so here my this is my own imagination. Okay, so I went over several problems, and I've tried to identify situations where it works and it doesn't work. Okay, so there are other problems. So one, for example, is optimal transport. So if you do the Sinkhorn algorithm, which corresponds to smoothing by the entropy, it turns out that the asymptotic analysis on the impact of the smoothing parameter, the first order term is already exponential, okay, when you do Sinkhorn. So it's a case where it won't be useful on Sinkhorn. It would be useful on the dual of Sinkhorn. Okay, so if you want to estimate the Kantorovich potentials, this is useful. I think it should be useful for saddle point problems. Okay, I have not worked out the details, but clearly, if it works for Nestor smoothing, there is a good chance that it should work for also for extra gradient, but I didn't check. And there are probably other possibilities which I've not thought of, but anywhere where you have an algorithm or a method that's doing approximation with a well-identified parameter, okay, like iteration number or step size or regularization parameter, there are ways of doing it. Thank you for your time.
A quick question. So do you think that maybe a mixture of both the approaches, like regular and Richardson, maybe at the start do regular and then move to Richardson, or like do a mixture of both the things can help?
Can you repeat the start of the question? I didn't get it.
So I'm saying, like, rather than doing Richardson for k goes to 0 to all the way of iterations, can you do a mixture, like maybe at the start regular and then switch to Richardson?
No.
Or maybe
I think the answer is with tail averaging. Why is tail averaging going? Let's go back. Okay. So the answer with tail averaging, because here it's known that doing averaging from the beginning is a problem. Okay. So here, if you want to do averaging from later on, you could. Okay. So if you want to start Richardson for after a while, of course you could. But then it does add some parameter. So for example, if you do like a AGD on a final data set, you could imagine that you start doing it after a single pass. Okay. Because yeah. Now, of course, you can all the tricks that people used already can be used, and indeed you can start from for a while. Indeed, so when you see like in simulation where it's not helping, here, yeah, clearly here you lose a bit, and you may want to avoid that. But yeah, sure.
okay. Yeah, because in the Nesterov smoothing, the graph that you showed.
Mm-hmm.
So yeah, this one, yeah. So if you see on the right hand side, maybe at the start up to like 3, like maybe you can use the regular one, and after 3, maybe you can switch.
Yeah, but here, okay, so here, what's happening there is, you see what I mentioned is that the three curves, they start at different points. Why? Because I need more iterations when I do extrapolation. For regular, I need 1. Richardson, I need 2. This one, I need 4. Okay, so that's why they are like décalés. How do you say in English, décalés? Okay, they are décalés. Shifted, yeah, multiple synonyms. So they are shifted by a constant factor. Okay, so here, the difference here is just due to the fact that you're using more iterations. So that difference is being kept for a while, and that difference gets annihilated after a while.
Okay.
But yes, I think it's more here the effect that you need more iterations. I could have started the curves all together, but I think that would be, I'm already cheating. That would be like super cheating.
Yeah. Thank you.
All right. So thanks, Francis, for this very interesting talk. So I think we have the virtual clap, the usual.